So, last time we consider forces on bodies of revolution of arbitrary profile in axial symmetric flow, and we computed the drag force that acts due to the pressure distribution for this flow. Of course, there is a base drag component which we said cannot be evaluated from any inviscid flow theory, and we saw that there for a pointed body the drag force depends on the variation of cross sectional area. Next, we will consider when the body of revolution of any arbitrary profile is not in axisymmetric flow, that is the body is non-axisymmetric flow, or we will consider the forces that acts when the body of revolution is in E to the flow. And so, we will be determining what are the forces acting on this body when the flow is like this. However, the geometry of the body still we will be considering symmetric, but the flow is not along its axis. Consequently, as we have seen earlier that it has a cross flow component and an axial flow component, which we earlier mentioned as u a and u c. And we saw that the solution is the complete solution is axial contribution and a cross flow component. So, similarly, the force also can be written that force due to this axial component of the flow, which as before will be the drag force only, which I have already evaluated, and again force due to this cross flow component. Now, we have earlier seen that the cross flow solution is given as cos theta d phi a dr, that is once the axial flow solution is known, we can straight away get the cross flow solution. Now, in this context we may remember that this axial contribution, that is phi a, which is the solution for axisymmetric flow, represents potential due to a source distribution. Phi a, this represents potential due to a source distribution. Now, since the cross flow potential is simply that a derivative of this cross flow potential, which is potential due to a source, and we know that the derivative of potential due to a source represents potential due to a doublet. So, this implies d phi a dr is potential due to doublet. And since this cos theta d phi a dr So, cos theta d phi a dr can also be written as d phi a dz, which implies that this doublet distribution has its axis along z. So, d phi a dz, this is potential due to the doublet with axis along z. Or we get that the cross flow potential then is represented by a doublet distribution with axis along z. And as you have seen here that the axial flow do not produce any lift force, but produces on of course drag force in this case, but no lift. And from this cross flow, it is obvious that this cross flow is going to produce even a lift, and we come back to our known fact from incompressible flow that a source distribution can be used to represent a non lifting flow, while to model or represent a lifting flow, a doublet distribution is required, where the doublet axis is normal to the flow direction. Now, to carry on further, let us say the velocity at any point on the flow at any point, say P is given by V, which is the undisturbed axial component of the free stream plus perturbation along x along the axial direction plus the cross flow component or in the radial direction plus perturbation component in the radial direction plus tangential component or swirl component of free stream as well as the perturbation. This is of course V square. And we have already that u a is u infinity cos alpha and u c is u infinity sin alpha are the cross flow and axial component of the undisturbed stream. Now, we will make an assumption that alpha is small, and consequently, this term wise, let us say term wise u a plus d phi dx. We have not yet split it in two part, that is axial and cross flow potential, but anyway we will subsequently do it. And let us say we are interested in the body, that is on the surface. This of course is independent of the body coordinate. On the body surface. Now, u a we substitute u infinity cos alpha and making small assumption cos square alpha can be written as 1 minus alpha square. So, this term becomes plus these are written as it is. For the radial component similarly, u c cos theta plus d phi dr and this can be written as u infinity dr dx square. This we obtained using boundary condition. Now, we have already seen that for slender bodies, this phi c, which is cos theta d phi a dr, and which for general slender bodies we have seen is given by f x by r cos theta. However, if you remember that for a cross flow for the axial flow, this f x represented the source distribution. However, now for phi c this must represent the doublet distribution, and we now give the standard notation for doublet strength, that is mu x cos theta. Which is doublet strength distribution. And as you have seen that the source strength in case of the axial part of the flow can be evaluated using the boundary condition, and which relates to the radius of the cross section or the cross sectional area. Similarly, this doublet strength will also depend on the boundary condition or can be evaluated from application of the boundary condition, and it must also relate to the cross sectional area of the and it relates to cross sectional area or radius. Now, if we apply the boundary condition, application of boundary condition gives us that u c cos theta plus d phi c d r on the body is approximately 0 and if substituted phi c equal to this term, so phi c equal to mu by r cos theta, then gives us that mu x is u c into r square, which is u c by pi a, where a is before the cross sectional area at a particular station x. And this then gives the cross flow potential to be mu cos theta by r, that is u c r square by r cos theta, and u c we can write as u infinity So, third term in that expression for velocity. So, hence third term in v square, which you have written earlier, is u c sin theta minus 1 by r d phi d theta. We have replaced the variable r by the surface radius and d phi d theta. Since phi a has no theta dependency, this d phi d theta is simply d phi c d theta, which can be evaluated from here, and this gives 2 u c sin theta square, that is 2 u infinity sin theta square into alpha square for small alpha. Now, knowing the velocity on the surface of the body, we can evaluate the pressure coefficient, and for that let us go back to that expression for pressure coefficient. Now, the expression for the pressure coefficient which we have derived earlier can be written in a more convenient form. Can be written in more convenient form, that is 1 minus plus which is up to second order accuracy as is required for axial bodies of revolution or axisymmetric flow cases. Now, this expression can then be written as on the body surface minus 2 by u infinity d phi dx on body plus alpha square minus dr dx square minus 4 alpha square sin square theta plus beta square by u infinity square d phi dx square on the body. And this is much smaller than the other term. So, this can be neglected. This term can be neglected. Now, this can also be written as that an axial contribution plus a cross flow contribution, an axial flow contribution and a cross flow contribution, and where this axial flow contribution is minus 2 by u infinity d phi a dx on body and CPC has minus 2 by u infinity So, we see this and these are just cross flow contribution and which comes only because of the body is in an angle of attack. This is of course, the familiar axial flow contribution and this has a combination of axial flow contribution and cross flow contribution. And now, this axial contribution to the pressure coefficient can give only a drag force as we have seen before. So, CPA, this gives rise to and this part we have already evaluated, which is that CD 1 which we evaluated in the last class, that comes from CPA. However, this CPC, the cross flow contribution, it gives both lift and drag. Now, using that expression for phi c which we have already derived, which is and making small alpha assumption, that CPC can be completely determined, which is minus 4 alpha dr dx cos theta plus 1 minus 4 sin square theta to alpha square. Now, this is the pressure distribution that, or the cross flow contribution of the pressure coefficient that acts on the body. So, once again considering a small segment of we will only consider the CPC, because this is already determined, and as because of this pressure distribution, there will be component of force which is in the normal to the surface area and which can be projected on different direction. So, the radial component of the force force on the elemental surface area is half rho infinity u infinity square C P C r d theta dx. This implies the cross force that is force in the direction of u c is half rho infinity u infinity square 0 to L this is what is the elemental area projected normal to radius. Now, this we can now substitute the expression for C P C here, which gives half rho infinity u infinity square into 4 alpha 0 to L 0 to 2 pi cos square theta into r dr dx d theta dx minus another term, this half rho infinity square we can keep like this, minus alpha square into 0 to L 0 to 2 pi cos theta into 1 minus 4 sin square theta r d theta dx. The integration can be carried out completely, giving n equal to half rho infinity u infinity square into alpha into 2 alpha into A B. A B is as before area of base. Area at L. We define a normal force component again based on the base area. So, that half rho infinity u infinity square A B equal to 2 alpha. So, this is what is the normal force contribution by the cross flow part of the pressure. This cross flow also contributes to the axial force. Now, cross flow also contributes to axial force. So, you see that the axial force contributes only axial force, but cross flow contributes both a cross force as well as an axial force, and the axial force due to the cross flow, let us denote it by A 2, where that drag force, or which we may now call in a generalized sense an axial force due to axial contribution as A 1, then we get A 2 equal to half rho infinity u infinity square into 0 to R L 0 to 2 pi C P C R d theta d r, where r d theta d r is the elemental area projected normal to axis. And once again, if we substitute this C P C, the cross flow pressure, the result comes out to be minus half rho infinity u infinity square into pi alpha square R L square or R B square. And an axial force coefficient C A 2 A 2 by half rho infinity u infinity square A B is minus alpha square. The C A 1 is eventually that C D 1 that we have axisymmetric flow case. So, when a body is in a flow which is not along its axis, or that is geode body of revolution, we see that there is two contribution to the axial force, one coming from the axial component of the force flow and another is coming from the cross flow component of the flow, and there is one normal force component coming from the cross flow. So, net axial force A 1 plus A 2 which can be written as half rho infinity u infinity square A b this is, as you remember, C d 1 plus C p b minus now, the lift and drag forces can be determined once the normal and axial forces are known. So, the lift force L is n cos alpha minus a sin alpha, and the drag force is n sin alpha plus a cos alpha. Or in terms of coefficients, C L is C n cos alpha minus C a sin alpha, and C d is C n sin alpha plus C a. And making the usual small angle of attack approximation, this can be written as C n into 1 minus alpha square by 2 minus C d 1 plus C p b minus alpha square into alpha. Now, we can make further approximation to this approximation and also substitute C n equal to 2 alpha. So, if we retain only the dominant terms, CL equal to 2 alpha and CD equal to CD1 plus PB plus alpha square. The alpha is of course in radian. Now, looking to this, we can say that the drag force coefficient alpha square that has arises only due to the cross flow contribution, or cross flow contribution also produces the lift. So, this part of the drag, this part of the drag is due to the cross flow and hence due to lift. So, this term is due to cross flow that produces the lift, and you see when lift is 0, this also becomes 0. Hence, this is called lift induced drag. Induced drag as alpha square. This drag also becomes 0. And if we compare this with for incompressible flow, compare this with the incompressible flow, incompressible wing CL square by pi aspect ratio, where this is wing aspect ratio. And even if we consider that in incompressible flow that CL according to the linearized theory over a flat plate becomes 4 pi alpha square. So, there is an aspect ratio term present here which was not here. Now, We also find that for the supersonic case, we have C d I by C L that equal to d I by L is alpha by 2. So, that implies the direction of the force vector due to angle of attack is midway between normal to the body and normal to flight path. So, that completes our discussion on the forces that acts on a body of revolution either in axial symmetric flow or in your case. We have seen that when the body is in an axial symmetric flow, then only a drag force acts, which of course depends on the variation of the cross sectional area of the body. While if there is a cross flow present, as in the non-axisymmetric flow case, we have both axial and normal forces. So, the total axial force in a general case comes from two sources, the axisymmetric component of the flow and as well as from the cross component of the flow. However, the normal force comes only from the cross component of the flow, and we also have seen that the induced drag in this case is, or induced drag coefficient is simply square of angle of attack expressed in radian, and the lift force approximately is 2 times the angle of attack expressed in radian. We also have seen that this cross flow potential can very easily be obtained from the axial flow potential. Eventually, this cross flow can be modeled by or is represented by a doublet distribution along the axis, while the axisymmetric flow is represented by source distribution along the axis, which confirms our incompressible flow analysis earlier, that non-lifting flow can be modeled by a source distribution, while a lifting force is to be modeled by a doublet distribution with doublet axis normal to the free stream direction. And that completes our force evaluation, force computation on bodies of revolution.